So this week we're going to talk about atoms, elements, and minerals. I'm also trying out this little notation here from PowerPoint. We'll see how that goes, and hopefully that's useful. So why do we care about these things? So what's useful about understanding atoms, elements, and of course minerals is that each has specific properties. And so if we understand the properties of the atoms, we understand the properties of the minerals when two things bond together to form something new, then we can use that to figure out potentially what minerals are in the magma that's forming this volcano. They have specific properties, and that potentially could tell me something about properties of the rocks, which then tell me something about how a volcano might erupt. Or certain properties of materials. It tells me how they might react under certain pressures and tensions. Or even how things might weather and erode, strength and things like that could give us something. So it certainly is useful. It's useful for hazards, geologic hazards. And of course it's useful to be able to identify minerals that are valuable. Titanium and gold and silver and all those kind of good things. If we know something about where they form and how they form, that could be helpful. So when we look at rocks, minerals, and atoms and the relationship here, we start with the atoms. And the atoms will bond together to form different minerals. And then the minerals will be a collection, and that'll form a rock. So really that's the big difference, right? So minerals are a collection of atoms, and rocks are a collection of minerals as a very general rule. And you could see with this rock called a granite, that the individual colors here represent different minerals. And then, of course, we could look even closer at these minerals and see they're made up of specific atoms that are bonded together. So just kind of reiterating that idea that we have two atoms here, silicon and oxygen. When they bond together, they form quartz, which is a mineral. If we take a collection of these minerals and they form an aggregate, we can get a granite in this case, a specific type of rock. So I just want to refresh your memory if you haven't seen this before, so you'll see it now, but you should have seen this in some chemistry class or physics class of some kind in the past. But we just want you to know the basics of an atom. So we're not going to get into the really gory details, but you should know a basic model like this, where every atom has a nucleus that contains protons and neutrons. The protons have a positive charge, the neutrons don't have a charge, and then there are electrons that are orbiting or circulating around the nucleus. And we draw it like this because it's easy to draw on paper, although this is probably more realistic where the electrons are moving around in more spherical and not in a specific path like planets around a sun. But it still helps us understand so we can kind of use that idea. So what we can gain from this is that the protons really dictate what atom or element we have. And so all carbon atoms have 6 protons. All hydrogen atoms have 1 proton. All uranium atoms have 92 protons. If you change the number of protons, you change what element you have. And so in a periodic table, we can see that the number here is referring to the number of protons, and it's its atomic number. So oxygen's atomic number is 8, and that also means it has 8 protons. And so it's kind of useful to be set up that way. We can identify the number of protons. Now, we did introduce the idea of an isotope in last week's module. It said that, look, we can't change protons because we changed the element, but we can throw in some extra neutrons occasionally. It changes the mass, but it doesn't change what it is. Now, not every atom or element has isotopes, but some of these isotopes are unstable and they can decay over time. We can use that to date certain rocks, and so we talked about that for absolute age dating last week. And so just to get, so this is kind of what we were talking about, or just a little review. So the isotope thing was just kind of, I just wanted you to be aware of that, and of course we talked about that last week. what we do want to know is how do we get these minerals? So we have these elements. In this case, we talked about silicon and oxygen. They bond together to form quartz. So how does that happen? Well, not all bonds are the same. The ways that atoms attach to each other are not the same. There's multiple bondings that happen. So here's the deal. I'm not going to go into detail, same thing. This is not a chemistry class. Just a little review. There's ionic bonds. These are where you have one atom is missing an electron, one it has one to give, and they move those around and it gives them a charge, and that charge makes them attract to each other. And something that you see and use all the time, salt, sodium chloride, NaCl, uses ionic bonds to hold it together to form something brand new, right? A chloride atom and a sodium atom separately are horrible, but together they form NaCl, which is salt, which is yummy. So ionic bonds is one way we can hold things together. This is where we gain or lose electrons, and that changes the charge, and we talked about the charge makes them attract. It has to do with the outer shell, same thing. This is just to show you what goes on here, where we can share or we can exchange or move electrons around to change charges. The periodic table is set up in such a way to tell you which ones gain and lose electrons, so we know that the ones over here and ones over here tend to bond together because of the electrical charges. There's also ways to share electrons where they don't actually leave, but they're shared. They kind of orbit around both. It's a little stronger, called covalent. Don't stress too much about this bonding stuff. I just want you to be aware that there's multiple ways that different atoms can bond together. Not all will bond with others. There has to be certain properties, sizes, the right number of electrons, whatever combination to allow these atoms to bond together in the proper way. Once they do, though, they form new things, new molecules, which potentially can be a mineral. So it's just like taking anything, and in some cases it's relatively simple. Oxygen and hydrogen form water, a new thing, right? A molecule. Sodium and chloride form something brand new. Silicon and oxygen form something brand new, and this mess of elements forms another mineral. So they bond together, we get something new. So what is a mineral? So what we're going to use is these 4 criteria to identify what a mineral is, because obviously there's lots of things sitting around. I have a pen in front of me. Is that a mineral? It's bonding of different atoms together to form material. My mouse, is that a mineral? My dog, these. So how do we know? Well, here's the criteria. It has to be naturally occurring, so it can't be man-made. So I've ruled out my mouse and my pen. Has to be inorganic, which means my dog can't be a mineral, so we've ruled him out. It has to have an orderly internal structure, which basically means it has to be a solid. So water can't be a mineral. And it has to have a definite chemical composition, which means you can't change it and still get the same thing. So SiO2 is the formula for quartz. You need 1 silicon atom, 2 oxygen atoms in a certain way to bond together to form quartz. You can't get quartz any other way. So it has that one particular structure always. So we need to use that to identify our minerals. Now there are, of course, because everywhere there's exceptions to the rule, and here it is, you can have mineraloids. And so opal, you've probably seen that before, is one of these that meets all of the criteria because it doesn't really have an orderly arrangement because there's some water and weirdness in there. Same thing, just want you to be aware of it, but don't worry about it. There are lots of minerals, 3,500 at least. Lucky for us, there's only about 20 minerals that make up 95% of all the rocks. And so all those other ones are super rare or only occur under very unique conditions. So we don't have to know all those. We just want to know some of the basics. So how do we identify what a mineral is and give it a name? We use the physical properties. So once we've decided that it's a mineral, it fits those 4 criteria, we would actually do a test. So as a geologist in the field, you would perform a couple different tests, and then if you weren't familiar, you'd bust out your little chart and you'd go through the chart and say, oh, if it's white, it can only be these minerals. And if it has a certain shape, it can only be these minerals. And then we could go through each property and we would narrow it down until we're like, oh, this is quartz. And that's how I know it's quartz. Then after you see it a couple bazillion times, you're like, oh, you don't need the chart. But for now, we would go through this chart and look at the different properties. So I just want to run through some of those properties with you. So color sometimes can be helpful, sometimes horrible. So there are certain minerals that are only one color, and that's useful, or they're unique color. Purple, not very common in the mineral world. Amethyst, boom, I'm good. Sometimes quartz can have multiple colors, and then it's hard to figure out what it is. So it can help, but it is a property that we would use to narrow down what it could be. Something called luster. So if it looks metallic, there's a lot of minerals that have a metallic sheen to them. We'd put them in a category, and then we'd work our way down to other properties. Or if they're glassy. Streak. Sounds kind of weird, but basically this is a ceramic plate that you would have with you in a lab. And you would take your mineral and you would scratch it, and the color is indicative of specific minerals. Some don't have a streak, some have unique colored streaks. So sometimes they don't kind of match what they look like, and so that can be helpful if it's very distinctive. Hardness, how hard the mineral is. And so there is a scale called Mohs hardness scale, and it's rated from 1 to 10, 1 being soft, 10 being the hardest. And we can use that to sometimes figure out what we have. And so these are the relative hardness of specific minerals that you might see. And in the field, how would we do that? We'd use these things right here on the right. So your fingernail is roughly 2 to 2.5 on the Mohs hardness scale. A coin, a steel knife, glass. And so if I'm trying to identify quartz, it has 7. My steel knife would not make a mark on quartz. But on calcite, which is also very common, I should be able to leave a mark. And so calcite and quartz can look very similar. So I would take out my knife and try to scratch it. If I can scratch it, it's probably calcite. If I can't scratch it, it's probably quartz. And that's how we would use the hardness potentially to identify a mineral. The crystal shape, which isn't always apparent, but can tell us something about the mineral. It has a specific shape to it. Is it a cube? There's some minerals that grow in cubes, right? Pyrite grows in cubes. Salt is cubic. Now, you can't always see it, and sometimes as minerals grow in tight spaces, they don't pick out when they're competing for space, they overlap and you can't really see it. So that's not always a great indicator, but when you can, it can be very helpful. So I'm going to run through these, same thing. This is a part you can glaze over, don't stress about. But there we can identify specific shapes based on how the atoms have bonded together. And of course they're labeled isometric, tetragonal, hexagonal, orthorhombic, monoclinic, triclinic. Yay! Some of that's related to how the rocks will break. And so another property is what's called cleavage. And so that means that if I strike the mineral, it will break in a specific way or specific angle or shape. And usually that's related to bond strength. And so if there's a weak bond in a certain direction, it'll break along that plane. And so we can use that to help us identify specific minerals. And of course, they can break in certain shapes, cubic shapes and things like that. Some have no cleavage whatsoever. When you break them, there's no preferred direction, and that's unique to a specific set of minerals, and quartz is one of those. Biotite, which is mica, is peelable, actually. You can peel it apart into these planes, almost like paper, because they have a very weak bond in that kind of connection between the sheets. Let's see, what else I got for you. Yeah, you can have multiple ones, sorry. So you can have cubes, you can have squished cubes like this. You can have really weird shapes, and this has to do with, same thing, the weakness in the bonds. Then there's something called fracture. We talked about where it doesn't have a cleavage, it's just an irregular breakage. And that's really common in quartz. This is I don't think it's on here, but it's called, oh, there it is, conchoidal fracture is the way it breaks because it has no weakness there. So that's what quartz does typically. Then there's specific gravity. It's really related to the density of something. So how heavy it is, we would compare it to water. So we could measure that, not necessarily in the field, but in a lab, and use that to figure out what we have if we're really baffled by, we couldn't use the other properties to help us with that. And then, of course, you get some unusual properties that only work for certain things. Yes, taste, like halite, that's a mineral. It's salt. It tastes like salt. Not the recommended way to identify minerals by licking them or tasting them, but it is doable. Some have a certain odor that you could do. Some have these really unique, what are called striations, which are how the mineral grew. Some are magnetic. And so there's mineral magnetite. So if we have a magnet, we can go around and pick it up, and then we would know that it's magnetite. So some of these are really, because they're unique, they stand out. Some double refraction, calcite, another one that's kind of unique. We can also X-ray them. So if we're just like, I have no idea what this is, we can take it back to the lab and put it in a machine and get an X-ray diffraction, and it would tell us specifically what it is. There are some chemical tests we could do, and the most common one we would do is use a weak hydrochloric acid solution. We put that on the mineral calcite. And calcite is a base, and the acid react, and they fizz or bubble. Now that's really important because calcite is super common, and it forms the rock limestone, which is extremely common on the surface of the earth. And it's an easy test. We carry a little acid bottle. It's very dilute, so it doesn't eat your skin away. We put a little drop on the rock, and it would bubble and fizz, indicating that there's calcite there. And that could suggest, of course, that we are looking at a big limestone layer, something like that. So the last couple things I just want to talk about is there's groups of minerals that we can look at. And so here they are. Here there's oxides, sulfides, sulfates, halides, carbonates. The most common group is the silicates. And why is that? Because oxygen and silicon are the most common elements in the continental crust, which is a big part of the earth where we see lots of minerals and things like that. So silicates are really common just because of the supply of the material that's available. Here's the other common ones. So you can see we did say there's 3,500 minerals. Luckily, there's not that many that are common or abundant, so we don't form so many that we can't figure out what they are, because the really crazy ones are rare. Okay, what else we got? Oh yeah, so there's the different mineral groups. Because silicates are so common, we talk about those more than anything else, and because they show up in igneous rocks all over the place, they're silicate minerals that form igneous rocks. The building block of what's called the silicates is a silicon-oxygen tetrahedron. Holy crap. Okay. So we said that quartz is silicon and oxygen. It's SiO2. This is a silicon atom surrounded by 4 oxygen atoms, and it forms almost like a pyramid. That is part of the formula for silicate minerals. So then there's another component that bonds to that and forms a specific mineral. And so what we see is like iron and magnesium can bond with that SiO4, that tetrahedron, and form a mineral called olivine. And so we can then have other elements bond with it and then form different minerals. And what we see is we get these groups where we have just like an iron atom bonds with a silicon oxygen tetrahedron and forms this isolated structure. But we get groups where they chain together, or double chain, or sheets, or form a framework. And these, the way they bond and form together, also dictates their properties. These sheet silicates in particular show a weakness between the sheets. That's that mineral mica that peels away and breaks. And so here's an example here. So this is a sheet silicate. And so this is trying to represent the silica oxygen tetrahedron. These are the other atoms that are bonding these two sheets together. And this is the weak point. So we can peel away at these particular places just because of the structure of the mineral. And so knowing something about the structure of the mineral can tell us some of its properties. And here's just another example. These are really common silicate minerals that we see. You'll see these next week in igneous rocks when we talk about that. There are the olivines and pyroxenes, micas, quartz, super common. These are what's going to show up in our igneous rocks. And the minerals themselves have these different silicate structures. Ones that are sheets that peel away, ones that fracture in 60 degrees or right angles, and ones that don't fracture very well at all, like quartz. And so the last thing here, yay, you say, the last thing is something that's called the Bowens reaction series. And this is basically just introducing you to the transition here from our minerals, understanding minerals, and how they apply to the rocks. And so when we look at igneous rocks in particular, they have a specific amount of these minerals in them, which helps us identify what they are, and they behave differently. So there are rocks that have these compositions, and we'll learn these terms next week. But the rock that we're going to call mafic would have minerals that run across like this. It would have lots of calcium feldspars, maybe some amphiboles and pyroxenes. But it wouldn't have a lot of this material here. And so we could tell something about how that rock might behave based on its mineral composition. And same with rocks that we're calling felsic. They have lots of these minerals here that are at the bottom. And so we could tell something about how this rock might behave based on its mineral composition. So this is how we can kind of draw you in and say, look, we're relating minerals. Learn something about minerals. Oh yeah, and guess what? That applies in the future when we talk about rocks. And not just igneous rocks, sedimentary rocks, even metamorphic rocks. Because once again, the minerals have certain properties, and they're going to affect the properties of the rock. So we'll keep that in mind as we move forward. And as always, if you have any questions, please feel free to contact me.